Hello, my name is Adrian, and I'm going to explain a little bit what our project is about. As you can see from the title of this video, this project is about the quantum harmonic oscillator, and so we need to cover a variety of points. First of all, we will start by explaining the deduction of several equations that are really important. For example, firstly, we will talk about the Schrödinger equation and then about the Dirac's equation. We are also going to talk a little bit about the Klein-Gordon equation, but that will be later on in the video. Then we will explain the Schrödinger equation for stationary levels of energy. We will make use of an application through the separation of variables. After that, we will define some new operators that are going to be very useful when talking about the Hamiltonian of the quantum harmonic oscillator. Later on, and by still making use of these new operators, we're going to define more operators, such as the number operator. And after that, we will find the relationship between these new operators and the eigenvalues of the Hamiltonian for the quantum harmonic oscillator. After that, we will find a general expression for these eigenvalues, and later on, we will explore the wave function for the ground state. And then finally, we will use the Harmonic polynomial to find an algebraic solution to the quantum harmonic oscillator. Finally, and to finish our video, we will talk a little bit about the Klein-Gordon equation, and then we will do a little discussion about if time is emergent or not. And so we will explore different points of view, such as the relativistic point of view or the quantum point of view, and then even from the thermodynamics points of view, okay? And so this is a presentation, and we hope that you enjoy it.
Deduction of equations, the Schrödinger equation. Starting from the wave-particle duality, we can understand that each particle has associated a wave function, which represents its amplitude probability, psi, which means that we can determine the probability of finding the particle in any point of the space. And finally, we can summarize the Schrödinger equation as where H is the Hamiltonian operator, which represents the total energy of the system, kinetic and potential energy, and we can write it as E is the energy of the system and nabla is the Laplacian, and its expression is. But our deduction will start from the wave equation, which, considering a single spatial dimension, is, if we derive it with respect to time and space, we obtain this. Now we are going to convert our classical magnitudes into operators, which is the formalism of quantum mechanics. And first, we have the energy operator, and this is the Hamiltonian, but we are going to rewrite it in order to simplify the notation. Also, we have the linear momentum operator, which is, if we clear from the derivative respect to time, we obtain this, being E the total energy of the system, kinetic and potential energy. And as we said before, each of our classical magnitudes becomes an operator, and the same happens to kinetic and potential energy. considering that the classical kinetic energy can be expressed as a function of the linear momentum as, we can rewrite it as an operator in terms of the momentum operator like this. Finally, if we substitute the expression of the energy operator, which is the sum of the kinetic and potential energy operators, we obtain the general time-dependent Schrödinger equations, which is finally this. Most accepted interpretation of the collapse of the wave function is given by the Copenhagen interpretation, which postulates that when the particle is measured, the wave function collapses, and then we can locate the particle at a certain point of the space. On the other hand, the square of the wave function represents the amplitude of probability of finding the particle at a given point in space.
Let's start with some historical context. To explain the phenomena of the subatomic world, two theories based on entirely different fields of mathematics appear almost at the same time. On one hand, we have the Schrödinger wave mechanics, and on the other hand, we have the complex mechanics of Heisenberg. In 1926, Schrödinger published his famous equation that we just proved, on which are the basis of, as we know today, the quantum wave theory. His work pleased many physicists because it helped to understand the unknowns of the early stages of the quantum theory. The thing they liked the most was precisely the ease of understanding the underlying mathematics. 6 months earlier, Heisenberg had published the very first paper of what we now call the quantum mechanics. But unlike Schrödinger's easiness of his function, he used a very much complex mathematics, the matrices. And this is the reason why we now will demonstrate the Dirac's equation, since it proves that both formulations are equivalent, unifying them with special relativity in a quantum relativistic equation. To do this, we must first derive the Klein-Gordon equation. I'm going to do a quick demonstration of how we will arrive to the Klein-Gordon equation. So, while in classical mechanics we define the kinetic energy as this, in special relativity the total energy of a system of particles is defined with this new equation. We need also the operator equivalents of the Schrödinger theory, which are these. And with all of these terms, if we rearrange them, we obtain the Klein-Gordon equation, which is this. This equation represents a free scalar field in the quantum field theory, successfully describing pions and particles of spin zero, such as bosons. However, it has some inconsistencies, such as, for example, it doesn't describe particles of spin 1/2, such as electrons, and also because it is square, this causes that it has two solutions, and one of them is negative. We can translate this term as the probability of finding a particle to be negative, and this is impossible. To solve these problems, Dirac proposes to linearize them, starting with the Klein-Gordon equation and demanding these facts, which are the Polish matrices and are consequence of applying the relativistic properties into the quantum. And with that, the equation of Klein-Gordon comes to this. But we can see that if we take alpha and beta as constant, the equation has no solutions. So Dirac's proposes to consider them as matrices of second dimension, such as these matrices. And if we rewrite the second equation, we come to these new terms. And if we apply the properties of relativity, we arrive to this, which is basically the Dirac equation, which can be also rewritten as the Dirac equation has also two solutions, and one of them is negative. This can be translated as for particles with properties analogues of those of the standard model, but with opposite electric charge. This is called the Dirac sea, and these particles with analogous properties are called the antiparticles.
Now we are going to see an application of the method of separation of variables for the partial derivative differential equation in order to solve the Schrödinger equation for stationary states of energy. So let's consider the Schrödinger equation for a system with a particle with mass m, velocity v, and with linear momentum p. And also we are going to consider a potential which doesn't depend on time. So the Hamiltonian is, and we can rewrite the Schrödinger equation as this equation allows only one solution by the separation of variables method, and for this method we have to express our function as a product of one function depend on space and one function depend on time. Therefore we obtain this. Because of psi doesn't depend on time, we can rewrite the equation as, if we pass to the right the term that depends on space and to the left those that depends on time, we get this, where E is a constant of separation with energy units. And with this, the following equation that we obtain are these. The first equation has a solution of the form, and the second one is an equation of eigenvectors, which is called the Schrödinger equation for stationary states of energy, or time-independent Schrödinger equation. Finally, the solution will be of the form, which are called stationary states of energy. They are eigenfunctions of the Hamiltonian operators, corresponding to the eigenvalues E. And in a conservative system, they are the solution of this equation, and they also verify this. So they are eigenfunctions of the energy operator with the eigenvalue E.
Yes, effectively. Years ago, when I was so little, I started with atoms. Fuck! My glasses have fallen because of the fucking hydrogen! But now I have grown up and I have a much wider perspective of physical laws, so I have seen that there, the Schrödinger equation applies too. For example, it is not for being rude, but if I know Ford, there, the Schrödinger equation applies too. But today we will better resolve the quantum harmonic oscillator. Yeah.
Hello, my name is Adrian, and I'm going to talk about the Hamiltonian of the quantum harmonic oscillator, and then I'm also going to define some new operators that we are going to use on the video. And so, first of all, we should start with the mathematical expression for the Hamiltonian, H. And so we have H equals the operator P squared over 2 times the mass plus m times omega squared times operator x squared, everything over 2. And now, from now on, instead of saying operator p or operator x, I'm just going to say p and x, because it's going to be repeated many times in the video. And so, well, again, with this expression, we should know that omega equals the square root of the spatial frequency, k, over m, the mass. And now, with this expression, it's easy to notice that this expression is 2 terms squared. And so, by making use of imaginary numbers, as we have studied, we can factorize the expression as a squared plus b squared equals, parenthesis, a minus ib times parenthesis, a plus ib. And so now we are going to factorize both operators, p and x, with the help of other 2 operators. We're going to call a tilde and a tilde dagger. Okay, a tilde and a tilde dagger. Being a tilde the same as a number alpha times x plus I beta p. And then a dagger or a tilde dagger equals alpha times x minus I times beta times p, with both alpha and beta being real numbers. And so by multiplying a tilde dagger and a tilde, we get the following expression, which says that a tilde dagger times a tilde equals alpha squared times x squared plus beta squared times p squared plus I times alpha times beta times parenthesis x times p minus p times x. Okay, and if we look at the first expression, the expression of the Hamiltonian, we can see that a squared in this case would be m times omega squared over 2, and beta squared would be equal to 1 over 2m. And so now we get the following expression, this one. So we have a tilde dagger times a tilde equals Hamiltonian h plus I times the square root of m omega squared times, over 2 times the square root of 1 over 2 times the mass, and everything multiplied by the commutator of x and p. But we know what the commutator of x and p equals to. We know that it is equal to I times h bar, and h bar is it comes from the expression of the Planck constant. So h bar equals the Planck constant, but it being over 2 times pi. Okay, and so h would be equal to a tilde dagger times a tilde plus h times omega over 2. And because of this, we get that a tilde would be equal to the square root of m times omega squared over 2 times x plus I times the square root of 1 over 2m times p. Now, in order to factorize h bar times omega, we define another operator, which is a, and this operator doesn't have any units, in such a way that a tilde equals the square root of h bar times omega times this new a, and this will also be equal to the square root of m times omega squared over 2 times x plus I, the square root of 1 over 2m times p. Consequently, if we solve for the new a that we have defined, we obtain the following expressions for a and a dagger. And so we have that a equals the square root of m times omega over 2h bar, and everything multiplied by parenthesis x plus I over m omega times p. And then we have a dagger, and so a dagger would be equal to the square root of m times omega over 2h bar times parenthesis x minus, okay, this is very important, minus I over n times omega times b. And so with this, we finally reach the following expression for the Hamiltonian, which would be that Hamiltonian h is equal to h bar times omega times, open parenthesis, a dagger times a plus 1 over 2.
If we observe the definition that our classmate have just given to us, we can define the number operator. The number operator has the formula n equals to a dagger a. We can define the Hamiltonian with this formula. And in this expression, we look that the energy is quantified. It means that it only can have discrete values. The size of these steps of energy is h bar omega. Now we have a question. What's the physical meaning of this number operator? Well, this gives us information of how many parts of energy we can see in the system. This is the particle that we can measure. If we want to change the number of this pack of energy, we will use the operator annihilation and operator creation. Both of these operators we will explain with more detail at a later date. Because of the Hamiltonian is a linear function of the number operator n, they will be in common state and they will be diagonalized at the same time. Now we look for a common base where both of these operators are diagonal. And now we define also the operator n, and they are the states of the number operator, and they have the formula this form. We apply this n to the Hamiltonian and we have this expression, and we have the eigenstate of the Hamiltonian with this expression. Now we look who are those n. For that we will use the operator a and the operator a dagger. First of all, we look that the operator a commute, and we give also names to the operator a and a dagger. The operator a is the destined operate, and the operator a dagger is the ascending operate. Now we look here that the operator a commute, and we have to do this operation. We only need to calculate a dagger with a because the product of a and a is 0, because the product of an operator with himself is always 0. We will use also the operation that we did before, and it is x with p is equals to I h bar, and p with x is equal to minus I h bar. We look here the product of a dagger and a, and it's equals to minus 1, and we look here the product of n and a, which is equal to minus a, and the product of n and a dagger, and it's equal to a dagger.
Hey, I'm Ney, and now I'm going to talk about the eigenvalues of the Hamiltonian and the quantum harmonic oscillator, but now in terms of the creation and annihilation operators. First of all, let's remember the mathematical expression of the Hamiltonian. As we can see, it is in terms of the constant of Planck divided by 2 pi, the angular frequency, and also the number operator, which we defined before. These operators are very important in many branches of physics. For example, in quantum mechanics, specifically in the quantum harmonic oscillator, and also in 20-particle systems, as well in the final quantum theory. These operators can be defined as operators that increase or decrease the number of particles in a system in a given state by 1. The ones which increase this number of particles are called creation operators, as well as the ones which decrease this number of particles are called the annihilation operators. In this way, creation operators are also called increasing operators, as well as annihilation operators can be also called as decreasing ones. These operators also increase or decrease the eigenvalues of other operators. I believe that in the beginning these definitions may seem a bit weird, but all of this has a mathematical meaning, so let's discover it, starting by reviewing these commutations between the creation and annihilation operators. Now we can commute the number operator with the creation operator and also the number operator with the annihilation one. The reason why if we commute the number operator with a dagger, we obtain a dagger, and if we commute the number operator with the decreasing operator, we obtain minus a, is that the terms involved in the commutation between the same operators run out. Now let's talk about this equation. Here we can see that the bracket notation is used, which is very important in quantum mechanics. Also, we can see that the product between the number operator and the creation operator can be expressed in terms of the product between creation and annihilation operator and commutation between the number operator and the creation operator. It is important to remark that this equation remains also correct if we replace the creation operator by any other operator. The deduction of this equation is very important to finally arrive to the mathematical meaning of the definitions of the creation and annihilation operators. So, first of all, we are going to consider this commutation between the number operator and the creation operator. We saw before that this was equal to the creation operator. Here, we can see that this commutation is also equal to this. We can be aware that the commutative property doesn't verify when we multiply two operators. Now it's time to see the mathematical meaning of the definitions of the creation and annihilation operators by obtaining the eigenvalues of the mathematical expression of the Hamiltonian in terms of those operators. First of all, we are going to commute the number operator times the creation operator over the ket n. If we apply the information I explained to you before, we finally arrive to the eigenvalue n plus 1 applied over the creation operator times the ket n. Similarly, if we apply the product between the number operator and the decreasing operator, we finally arrive to the eigenvalue n minus 1 applied over the distraction operator times the ket n. Since we had got the eigenvalues in terms of those new operators, we can be aware of the mathematical meaning of the definitions I had introduced to you in the beginning. That is the reason why creation operators and annihilation operators respectively increase or reduce the number of particles of any system or the eigenvalue of any other operator. After watching this information, now it's time to see how do creation and annihilation operators behave over the eigenstates of the number operator. Now it's time to deal with the proportionality between these operators and the eigenvalues we had got before. First of all, we are going to solve this equation, solving the value of the constant c in terms of the positively defined norm n. How do we do this? Let's see this. Here we can see that the number operator is between the bra n and the ket n. It is important to remark that there is an important property of dual spaces when we use the bracket notation. For example, if we apply to the distraction operator applied over the ket n a dagger, we just obtain the bra n applied over the other operator, the creation operator. So it is very important to focus on this property when we work with this notation in quantum mechanics. Finally, after talking about this, we obtain the constancy in terms of n like the square root of n. Let's do the same, but taking into account the proportionality between the creation operator and the eigenvalue n plus 1. In this case, we have the product between the destruction operator and the creation operator, and all of this is between the bra n and the ket n. This product can be expressed in terms of the computation of these two operators. In the beginning, we had worked with a similar expression, but with the product between the number operator and the creation or destruction operators. I don't remember now. And finally, in this case, we arrive to this, where we can see that in terms of n, c prime is equal to the square root of the eigenvalue n plus 1. It is important to remark in these cases that the constant belongs to the field of the positive real numbers.
Before the next step, we should have in mind that as n is equal to this expression and bra of n multiplied by a dagger and a multiplied by ket of n, they both are norms. Having in mind that norms have a property that they always are equal or greater than 0, we then know that n must be equal or greater than 0 too, because it is a construction of a multiplication of two norms. And now we will see why this is important. Having it in mind and applying a circumflex over the previous expression, we now have a recurrence. We have this expression, and so on. But we have a problem when n will be equal to a negative value, because as we have said before, n must be or positive or 0. And to avoid that, we determine that n must be a natural number. In order to, at a certain point, we will have a 0 somewhere, and it will truncate the whole expression, avoiding that negative values. So, as it is written there, n must be a natural number in order to this recurrence, and the previous condition are true. This state where n is equal to 0 is the ground state, and it has the lowest energy of all the states, and from there we can obtain the rest of the expressions of the recurrence. Then applying the recurrence from the ground state where n is equal to 0 to the nth state where n is equal to n, we arrive to a general expression, which is very useful, as it is said at general, because if you substitute n to whatever number you want, you will arrive to that state. For example, if you change that n by 3, you will arrive to the third state.
Now we are going to talk about the wave function for the ground state. The ground state of a quantum mechanical system is its lowest energy state. The energy of the ground state is known as the 0 point of the system. In quantum field theory, the ground state is usually called the vacuum state or the vacuum. The representation in space of the ground state will be obtained on the basis of the descent operator, which applied to the 0 ket should be the null ket. This is because the descent operator makes the eigenvalue decrease by 1. If we apply this hypothesis to x prime and we switch the descent operator with its expression, which is the square root of m times omega divided by 2 times h multiplied by x plus the coefficient of I times p divided by m times omega, we get this expression. to which we are going to apply the identity property of x by prime, which is the integral of multiplying the ket x by prime until the ra x by prime equals to 1. This way we get this expression. Keeping in mind that the constant square root of m times omega divided by 2 times h has been eliminated because the first equation was equal to 0. If we now apply the product by gets and the distributive property, we obtain this expression. We must now remember that a quantum operator is the one that represents a physical quantity in the formalism of quantum mechanics. They must satisfy certain formal properties, such as being self-attached. Quantum operators arise because in quantum mechanics, nature is described as a wave function and not as discrete particles. Part of quantum mechanics is based on establishing operators associated with the parameters to describe the system. In this case, x, which describes position, and p, which describes linear moment, are, to our astonishment, position and moments operators, respectively, whose action is diagonal over the position basis. Therefore, the integral is rewritten as this. The integral can be now eliminated with a letter delta, arriving to a differential equation. Since the terms of the equation are adding up, we can solve the equation by taking one of the terms to the other side of the equality as follows. Now we integrate each side of the equation and we finally get this one. Where h divided by m times omega has been substituted by alpha sub 0 squared. It is easy to see now that the value for phi sub 0 is this one. This is because if we substitute this expression on the left side of the equality, doing its derivative and by the 3 hours later theorem, we can get to the expression on the right side of the equation. We can see here the process we have followed in order to check. Therefore, the expression we got after we integrated the differential equation has been verified, and the expression for phi sub 0 is right. C is a constant that has to still be determined by normalization, but this is a job for my following partner. This way, and according to the calculation we have made so far, we get this expression. Which is the solution for 0, the ground state.
We had previously deduced that our function had the following expression in its ground state. In this expression, a normalization constant c is included. This constant can be used to turn set function into one that expresses probability density in a way that the total probability is 1. Using this condition, we can compute this constant c. If c is real, the final result is, in which deduction we use the following consideration. But what does it mean exactly to normalize the ground state solution in this physical context? Well, we must remember that without the normalization, our wave function represents a single-valued probability amplitude at a certain time and position. But after this normalization process, we get the probability of finding a specific particle at that time and position we previously mentioned. It's also important to note that the ground state energy of the quantum harmonic oscillator, that is, its minimum total energy possible, is not zero. The zero energy level is, in this way, arbitrary and gives no information about the system. This happens in almost all quantum mechanical systems and can be interpreted as all particles, even while considered at rest, have some kind of kinetic energy that is called zero-point energy. Given the final expression for the ground state wave function, we can easily compute it for the next energy levels using the previously defined ladder operators. Thus, the utility of the ladder operators is made present. Starting from a ground state wave function, is it possible to obtain an expression for excited states, that is, superior states of energy, just by applying the creation operator? We can also descend on the different energy levels with the inverse method by applying the annihilation operator. The role of these operators is remarkable in quantum mechanics, specifically in the study of many particle systems. Finally, it's possible to obtain a general expression for the wave function that acts as a solution of the equation we first proposed. The family of polynomials which appear between the normalization constant and the exponential function receives the name of Hermite polynomials and constitute the solution to the so-called Hermite differential equation. Using the definition of these polynomials, we can write the general expression for the wave function in a more compact way. The Hermite equation is a second-order differential equation. Therefore, it can be solved using the power series method that is well known in this physics course. Its coefficients can be determined in this way through a recurrence relation. Starting from the non-time dependent Schrödinger equation, we can also arrive to this expression using the asymptotic method. During the resolution process, we've seen that total energy follows this rule. But what does it mean exactly? Well, this is called quantization of energy. That is, the total energy of the quantum harmonic oscillator, potential plus kinetic, can't take any real value, but rather only certain ones that constitute their energy levels. This happens because total energy depends on a natural number n, as we can see in the expression.
The Klein-Gordon's equation was originally proposed by Schrödinger in order to apply the wave equation to a relativistic particle, in a try to unify the quantum ideas with Einstein's special relativity. But most of the problems which made this try fail came of dealing with phi as a wave equation, coming through the probabilistic interpretation, which had alongside a lot of internal incoherencies. For example, the equation is not definite positive, so we cannot interpret the square of the module as a possibility, making it not worthy to be used as a description of the relativity from the quantum mechanics. However, some problems have been resolved. For example, at first, from the first interpretation, as energy is not lower bounded, it would have made particles unstable. However, after some research and from the new interpretations, we have determined that this energy negative is in fact the representation of antiparticles in the equation. But after all, despite having failed in his main objective, it still is very useful in the quantum field theory, as it describes correctly the particles with spin zero. The Klein-Gordon equation is obtained directly from the relativistic expression of energy and momentum and the Schrödinger ideas. Applying the second equation into the first one and applying it a field phi, we then now have this expression. Here we have used phi as a field and not as a wave equation in order to avoid the previously said internal problems that have alongside the interpretation of the probability. And why we can do this? Well, This is because we now are immersed in the quantum field theory, where the important thing is not waves, but fields, the main fields instead, and how the space-time is modified by them. And by changing this, we now don't have a problem with negative numbers, because we're not talking about a probability. We can rewrite this equation in function of the development coefficients A dagger and A, and applying the Lagrangian, is this, from the minimum action principle, to a real field and with neutral particles, we then can rewrite the equation into this form. And now, by applying the operator formalism to A dagger and A, we reach to an equation which is formally similar to which one we have seen before at the quantum harmonic oscillator. And it's now when it is revealed that we can interpret the whole field as a set of infinite quantum harmonic oscillators. And this all is so important because this equation is very useful to describe particles with spin zero, as for example are pions or bosons, for example the Higgs one.
From a classical general relativity point of view, space-time is the medium used to describe any macroscopic phenomena. Therefore, space-time tissue gets perfectly defined using a four-dimensional Lorentz variety. We can get to the conclusion that this conjugates underlies all physics casualities, and it's not a byproduct of them. However, it acts differently from classical mechanics, because it's not an absolute background with perfectly fixed parameters, but rather a dynamic system. Since it interacts with other physical properties, such as mass energy and even with itself, we can get to the possibility of it being a product of certain casualties. This way, it is emergent and not fundamental. What is the point of view of space-time in modern quantum physics? To our astonishment, in quantum mechanics, time is an external concept that acts in an absolute way, much as in the classical physics. This is contrary to the character of space-time described in general relativity, and one of the many aspects in which general relativity differs from quantum mechanics. Nowadays, there are two fundamental theories that try to reunite both, and this discrepancy in time obviously appears in both of them. Now we are going to talk about the quantum gravity inspiration and how we are going to treat this concept.
The first arise quantum gravity theories, and even the later ones, were inspired by one specific expression, which is called the Wheeler-DeWitt equation, which from now on we will call it WDW for simplicity. Well, fundamentally it is the solution of applying the Schrödinger equation to the hypothetic wave function of the entire universe. Well, we do not talk about it as if it were a three-dimensional wave, but rather as a field of all possible configuration of space-time. Its solution is a wave function defined in a three-dimensional space which doesn't depend on time. In this deterministic equation, the geometry of the entire universe seems to be perfectly defined without the inclusion of time, which is a surprising result. Furthermore, if we apply momentum constraints to the WDW equation, we can obtain the Schrödinger equation. And well, this will mean that the Schrödinger equation is a particular case of the WDW equation and not the other way around. This issue has established the question of whether the WDW equation is a more fundamental equation than Schrödinger's. Of course, the WDW equation is not sustained in any experimental research data, and it could be only an error in formulation as far as we know, but the problem it describes continues to be relevant in the new models of quantum gravity. The questioning about whether time is fundamental or relative It's known as the time problem.
Most classical physics laws involving time have one thing in common: its reversibility. That is, we could introduce a negative time instead of the positive one established by convention, and they would be as valid as they were before. However, when we drop a glass of water to the floor and it shatters into 100 pieces, we don't usually see those pieces rearranged to form said glass, process that could be possible in terms of energy exchange. One concept, entropy, prevents this weird event to happen. The second law of thermodynamics establishes that any enclosed system evolves to the highest possible entropy state available. As a result, we could say that the only thing that separates future from past in a causal relation way is entropy, thus giving the universe a clear direction to evolve. We can talk then about the thermodynamic arrow of time. There are other arrows of time, such as the cosmological or even the psychological one, but most of them are a byproduct of the one previously mentioned. It's worth to be mentioned that we can talk about the universe evolving to a higher state of entropy because it's considered that the universe, in its origin, had its lowest entropy, thus representing this moment the point of comparison we will use from now on.